Got my trusty TI-30 X2S here, no big deal. The minus button isn't working, but on the plus side, everything else works. You ever wonder if you take a calculator and you press the buttons as fast as you can, don't you think it would become a calcul earlier? Alright, this is actually what I'm going to get my wife for Christmas. I'm going to get her some Pebbles and a bunch of calculators. You know, I figure it's the perfect Christmas gift. She's always telling me, like, it's the little things that count. Because, that's funny. I don't care what you say. Alright, do a little bit of calculus. Maybe I'll get all you guys a calculator for Christmas, but I wouldn't count on it. Alright, not a lot for you guys to go over on the online lesson here, but I want to make sure that this strategy doesn't disappear. Reminder, don't skip this step. Please don't skip this step, so you know where you're headed when you are done. So quick cross multiplication, a times x plus 2, b times 2x minus 3 equals the numerator. This is what we're trying to do with partial fractions. Let's plug in negative 2. We're going to get negative 4. Negative 4 minus 3 is negative 7 equals negative 14. B is going to equal 2. By plugging, what do I want here? 3 halves. This goes away. 3 halves here is going to be 21 halves. And 3 halves here is going to be what? It's going to be 1 1/2, 3 1/2, 7 halves. So we have 7 halves. A equals that, and A just equals 3. And don't forget, when we antiderive this, we're going to have a half come out in the chain rule. So we're going to need 3 halves this, and we're going to need 2 times this. So there's the only 3 halves that I see. So we are finished. Probably should have looked at that ahead of time. By the way, don't do this. Don't do this. Okay, so what are you guys doing today? So really quick, you guys are going to be looking at differential equations for the first time on the slope field lab. Alright, differential equations are just equations with a derivative. So some of these things we know a lot about because we just spent 2 months taking antiderivatives and understanding integrals. So this is an example of one that we know a lot about. Somebody took a derivative and got 2x. Well, we know the equation that came before that. The equation that came before that must have been y equals x squared. So some differential equations we're really familiar with. Others we know very, very little about. We have no possible way of anti-deriving this equation. There's no procedure that we can call upon. So what we use instead is something called a slope field to get information about the function that came before this. Or more than likely it's not a function. Actually, probably shouldn't have said that at all. Sometimes it will be, but not always. Okay, so how do we gain this information? Well, it's still useful to have information about this, even though we know what it is, because we don't know where it is. There's always this plus c going on here, so there's an infinite number of possibilities, even though we know the equation that came before this. But we have no idea what came before this. So what we do is we build something called a slope field, and this is what you guys are going to be doing in the lab. A slope field is a collection of little teeny tiny segments that represents what the slope of the original equation would be at that point. So I'm going to build a little bit of one here. I'm not going to go into detail because you guys are going to go up, you're going to do that in the lab. So what would the slope field look like for these two equations? Well, we're going to assemble all these mini tangent line slopes, and I'm going to put them into a table. Where am I plugging this stuff in? I'm plugging it into the differential equation. So I'm just going to pick some random points. I'm going to make them as simple as possible. Seems to me this would be the easiest coordinate, and then any combinations of zeros and ones and ones, those seem all very easy. But what if I did the same thing with negatives? There needs to be no order, no rhyme or reason to this. We're just trying to collect information. And it seems, well, why don't I do negative 1 and 1, and 1 and negative 1. So what do I do with all of these random numbers? Well, I'm just selecting these randomly. These are coordinates on the xy axis, picking whatever I want, started simple, and then I'll work harder and harder and harder. and I'm going to plug all of these values into my differential equation. Well, this one's only in terms of x. There is no y value here. So basically, the slope will be equivalent to 2 times whatever my x input is. Well, 2 times 0 is 0. 2 times 1 is 2. 2 times 0 is 0. 2 times 1 is 2. Negative 2, negative 2, negative 2, negative 2. And when I get to 1 comma negative 1, the y value doesn't matter. I'm still going to get 2. And these are the values that I'm going to graph. So at this location of 0 comma 0, what I do is I graph a little tangent line slope that has a slope of 0. So right here I put a little mark. Wow, that's off a little bit there, isn't it? It won't, I mean, are you serious right now? Well, here's what I'll do. I'll just drag. There, that's what we want. That was such a drag. So I want a little tangent line slope at 0, 0. I drew a little segment that actually had a slope of 0. And then I would go to 1 comma 0 and graph a slope of 2. Well, 1 comma 0 is right there. A slope of 2 would be kind of steep, like that. At 0, 1, I'd have 0. Another 0. At 1 comma 1, I'd have 2. Another steep one. At negative 1 comma 0, I'd have negative 2. That would go this way. And I just keep going. What about, oh, I did this one twice, didn't I? Well, I don't need you twice. At negative 1, I'd have another line that's equally as steep like this. At 1 comma negative 1, I'd have another line that's steep like this. And then what I start to realize is I don't actually have to make a table with 400 inputs. What I realize is the y value means nothing. So I can quickly fill in a lot of these just by checking the behavior of x. X will decide everything. If I plug in 1 for x, I'm always going to get 2. If I plug in 0 for x, I'm always going to get 0. And you can build your slope field, and you can start to collect these things really, really fast without having to actually plug them all in. In fact, it would be a waste of time to plug them all in. All right, let's look at our second slope field there, x plus y. So I'm going to do the same thing. This time I'm going to pick a few other random coordinates, but 0, 0 always seems to me to make sense. What if I did 1 comma 2, 2 comma 3, let's do negative 1 comma 2, let's do negative 2 comma 1, just making stuff up, 0, 2, 2, 0, 0, negative 2, negative 2, 0, just for fun. This slope field's behavior, the rate of change of whatever function came before this is how it's changing. So all I need to do is add my 2 inputs. 0 plus 0 is 0, 3, 5, 1, negative 1, 2, 2, negative 2, negative 2. So what would I do on my graph? I'm plotting these. These are the slopes that I'm plotting. So at 0, 0, I would plot a tangent line with a slope of 0. At 1 comma 2, I'd plot a tangent line with a slope of 3. Over 1 up 2, and then a pretty steep little dash there. This graph is probably too small. You're going to have to make little teeny tiny marks. It's hard with this marker, and I also wanted to stand out on the video. 2 comma 3, a slope of 5. 2, 3, a slope of 5 is so steep you really won't be able to tell that it's not a vertical line anymore. Negative 1, 2, a slope of 1. That looks more gradual, like so. And I don't necessarily need to plot all of these, but negative 2, 1 would be a slope of negative 1. So that would oppose that direction. And we just keep collecting these over and over and over again. This would be a slope of 2. This would be a slope of 2. This would be a slope of negative 2. And you guys get the idea. You're just collecting little mini tangent lines. And as you go, if you make enough of them, you start to realize they take on the behavior of the function you're looking at. I know the function that came before this was x squared, and see how the slopes look exactly like an x squared? That's why we use a slope field. All right, so this is the idea I'm hoping you guys are getting out of the lab, but for given some derivative, some dy dx, a slope field will allow us to see what the original function was, whether we can take an antiderivative or not. Whether maybe we know what came before this, maybe we have no idea, but we can always get a look at what we're doing by building a slope field, which is pretty fun. All right, so this slope field lab, this is a lab, it'll be graded as a lab, but this is due when I see you guys again on these 2 days. All right, so it's like a take-home lab, I guess you'd say. And yes, you do have to fill out every single one of the slopes on the slope fields. It's a lot of tick, 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 tick. So if you get ticked off, my bad. It's the slope field's fault. All right, but after this lab, I'll never make you do it again. All right, I'll see you guys in class.